The task is to create an audio dataset that can load arbitrary large audio from the disk. So in this case, I have a WAV file, which is an uncompressed format, and it can get really large. In this case, it is 3.2 gigabytes for kind of a 5-hour long audio. This could be a podcast, audiobook, or a speech. And we wish to load it in Python, turn it into a tensor, create a dataset out of it, and that dataset could be batched for downstream tasks like audio classification or audio generation. And for this, we need to pip install Torch and also Torch Audio. So you can do it outside Jupyter Notebook or inside. And after you do this, the next step is to load different chunks of this audio file. So let me first set the file name. Since it is in my working directory, I just can say data.t.wav. Now let's load the necessary libraries. So I'm gonna import Torch and Torch Audio. These are basically the two libraries that we're gonna work with. Also, it's always useful to, along the way, have a look at your audio, listen to it, and see if it makes sense. So Jupyter Notebook has this ipython.display, which can display different chunks of audio. I'm gonna import this. For the time being, let's first use Torch Audio.load, and by default, if you go to the documentation, it's gonna take the file name and some parameters, but by default, it's gonna load the whole audio file into memory. Most libraries do this, load the whole audio file into memory, consume a lot of memory, and then chunk it, batch it, and process it. We're not gonna do this. We're gonna load only chunks of this audio file. So I pass in the audio file name, and here we have some parameters called frame offset, for instance. Frame offset. If I set it to 0, it will start from the start of my audio file. It basically tells you how much to skip. The next parameter is number of frames. So num frames. Let me load for now 100,000 frames and see what it outputs. It's gonna output two things. One is the wave as a tensor, so I'll call it wave tensor. The other is the sampling rate of the audio. So after you run this, we can have a look at the wave tensor. As you can see, these are floating point numbers. You can ask for the D type. It's a float 32. So what Torch Audio does behind the scenes, it normalizes the audio by casting it into the float type. By default, digital audio is in integer format. So if I want to ask Torch Audio not to normalize it, I can set normalize to false. And if I have another look, it's going to be integer 16. It's important to have a look at the maximum value and also the minimum value of my original integer 16-bit integer. So right now the minimum is negative 7,068, maximum is positive 11,864. Now if you normalize it, so let me copy this chunk of code and set normalize to true, the minimum would be negative 0.21, maximum positive 0.36. Let's verify this. Let's see if what the mean is. It's almost 0. Let's see what the standard deviation is. It's around 0.04. So it's not exactly 1. But the values should be between -1 and 1. All right. Now the next step is to create a dataset class. I'm going to call it class large audio dataset. I'm not going to inherit from anything. I'm just going to create a pure Python class in this case. For my class right now, I will just create an init method and pass for now. Then I'm going to create a get item method, get item with an index, and I'm going to pass it for now. So it's always useful when you create a Python class that you're not really sure about the details of, to basically say, I want a class. I will need to initialize it with some values, and I want to have a method that will give me the item if I give it an index. That's how most datasets are like. They also have a len, so def dunder len. So when in Python you say what is the length of my dataset, it's gonna return the length, how many elements it has in it. I'm gonna pass it for now. So let's see what my dataset should do. Initially, it should take a file name like f and use torchaudio.load to load that file name containing my wave tensor and sample rate. not the full audio, which we saw is quite big, around 3.2 gigabytes. Not the full audio, but only a chunk of it. From a frame offset, or how much to skip, a number of frames, which would be our window. So here in initialization, probably one thing that I need is the file name. So I can store it in self.file name inside of the class, and that should be enough for now. So let me test out my large audio dataset. Let's call it my dataset, large audio dataset. And if I initialize it with fn, it now should have an attribute called fn, which points to my audio file. Now I needed to get the item every time I pass an index. But before I know how many indices we have in this dataset, I should figure out a way to get the length of the dataset. Okay, so to get the length of the dataset, we want to chunk our audio into window size chunks of audio. So if we have a look, this might seem confusing at first, but if we have an audio file, which is, let's say, 5 samples, and if I want to have a window size, let's call it W, of size 1 sample at a time. And if I have a stride of, let's say, 1, how many will I end up with? 1, 2, 3, 4, 5. Then if I make it a bit more complicated, I can say my window size, and let's change it. Let's use the same terminology we use for convolution. So let's call it kernel size, my K. If my K or window size is basically 2 now with the same stride 1, I'm going to look at windows of size 2, and I'm going to hop 1 sample because my stride is 1. Therefore, I will end up with 4, 5 and 4. I will basically lose 1 sample in the output, something like that. Now, if I make it even more complicated, so if it K is 2 and the stride is 2 with the same 5 samples, I'm going to start here, choose a window size 2, and for the next step, I'm going to jump 2 steps, get another sample, and if I want to keep the last chunk, I'll basically end up with 3. So 5 samples becomes 3 chunks. So the calculation could get a bit complex. Good thing is we can draw a 101 mapping into convolution 1D, one-dimensional convolution. If I go to torch.org, the Torch documentation, and read the documentation for conv1D, it does something pretty similar. The difference is we have kernel size, which we had called K, and stride. We don't use padding or dilation. Then if you scroll down in the output, you'll see the output shape is basically the input shape. So in our case, it is 5 plus 2 times padding. We don't have padding, so this part would be 0 minus. In our case, dilation is 1, so we don't have dilation. Kernel size minus 1 divided by stride plus 1. So if I write down this formula and I say out is basically in minus K minus 1 divided by S stride plus 1. You'll see that for all of these, the formula works. So out here would be kernel size. So 5, which is input, minus kernel size minus 1, which is 0, minus 1 divided by S, which is 1. We'll end up with plus 1. We'll end up with 5. Out here would be input, which is 5, minus K2 minus 1 divided by S, which is 1 plus 1. So here we get 3 plus 1, 4. And even for K2 and S2, this formula should work. So let's calculate. In is 5 minus K is 2 minus 1 is 1 minus 1. S is 2 now, plus 1 would be 3 over 2 plus 1. Now, depending on whether you want to keep the last segment, if it's not divisible by your kernel size, if it's smaller than your kernel size, you might want to treat this differently. So right now, if I want to keep the last one, if it's smaller, I would take the ceiling of this fraction. So I would say 3 over 2, the ceiling is 2 plus 1, 3. That's if I keep the last segment. If I don't wanna, so let's call this keep last. If I want to drop the last segment, if it's smaller than my kernel size, I will use floor. And in that case, 3/2 will be the floor of that, which is 1 plus 1. I'll end up with 2 segments, these 2 segments, and I'll drop this last one. All right, so let's implement this formula in our Python classes get, item, and also len. So in this case, I will basically implement this little formula over here in Python. So go back to the notebook. Now for the length, first things first, we need the length of the whole audio file. And for that purpose, we can use Torch Audio's info. Let's see if we can find Torch Audio's info. There we go. So Torch Audio info gets a file name. Optionally, you can pass in the file format. If you are using specific format and the backend cannot recognize it, like MP3, M4A. Buffer size determines how much of the audio to buffer. This is for larger audio. It's not necessary to change this for our use case. Now it will give you some metadata. Let's try it out first. So torchaudio.info and pass in my file name. It's going to give you an audio metadata object. So let's call it metadata and let's have a look at its attributes. It has an attribute called encoding. Our file is WAV file, so it is PCMS. It has channels. Ours is studio, so it has 2 channels. We probably could verify this here in the wave tensor as well. The little chunk that we imported, we can have a look at the number of channels. It says it has 2 channels and 100,000 samples because we asked for 100,000 frames. Let's have a look at other attributes, number of frames, which we verified, and the sample rate. Now, what we're looking for is the number of frames. Our original audio has, let's see, 842 million, almost, different frames. So that's the length of our audio file. So let's call it fn_len. Let's just copy this chunk of code and say, what is the metadata of the audio that we just added here, and use torch info, pass in the file name, get the metadata stored, and from this metadata, I'm gonna ask for the number of frames. Let's quickly verify to see if my data set now has this fn_len, and that's correct. I always just want to keep this consistent with the original syntax. So if somebody else comes in and wants to have a look at my code, knows what each class attribute means, so I can potentially change this fn_len to number of frames or total number of frames, something that would make more sense. So I'll do this here. Say this is called number of frames. Now, in the 101 mapping, this would basically be my the input length, number of frames in the formula. To calculate the length, I can either create a new method like so. Def, let's calculate number of chunks. And it's simple methods that will return the output of this calculation. Input minus k minus 1 minus 1. If we want to have a k and an s window size and a hop length that are consistent across our calculations, we can ask for it in the init of our class. So I can say my window size, which is basically my k. Let's say I'm going to use 3 seconds of audio. This is arbitrary. And my stride s, or I can call it hop length. This is more common for audio. Let's say my hop length is 1 second. Put them as floats, just to remind ourselves that these are floating points. Then I can store them as attributes. So self dot window size set here, self.hop length is also set. Now, if I want to calculate the number of chunks, I'll basically need to calculate, let me write down the formula. So input minus k minus 1 minus 1, this whole thing divided by s, and eventually 1 added to it. In terms of our code, the input would be number of frames. So self.num frames minus, well, we have 2k minus 1, so basically I can say this minus 1, let's go to so this minus 1 and this minus 1 will cancel out because this will become plus 1. So I can kind of simplify this by saying my input minus the window size divided by stride and plus 1. So self number of frames minus self dot window size, put them in parentheses, divided by hop length, so self.hop length, and eventually +1. I want to return this, and that's calculating my total number of chunks. So I can say return. So we didn't need to really put it in a separate function. If we want to use it multiple times, it might be a good idea. So return self.calculate number of chunks, and let's see if it works. So my data set, I can ask for either calculate number of chunks. In this case, let's see what it returns. It says your hop length is 1. So it's basically only going to remove window size and add 1 to it. It's going to use only 2 frames. But if I set the window size to 3, but the hop length to 2, so to jump every 2 seconds and calculate the chunk, it's almost going to be cut in half. So by 3, it's going to be cut in thirds, and so on. Okay, so we have this formula that's working. Now, we need to get an item from our data set. Our items index should basically be data set number of frames. But actually, since we have the length of our data set, so I can say what is the length of my data set. Here it says float cannot be interpreted as an integer. One thing to fix here, because when we said data set calculate number of chunks, right now is using float. So we have to go back to this point that I mentioned here when I said, do you want to keep the last or do you want to drop the last? If you want to keep the last, use the ceiling and basically turn each fraction into the larger integer next to it. And if you want to drop the last, use floor division. If I want to keep the last chunk, I would basically say here, wrap this whole thing around a ceiling function. In Python, we have multiple ceiling functions. The most common is from the math library, which is built in. Let's have a look. So math.ceil returns the ceiling of x. Let's try it out. So let's say 1.1. It will return 2. That's the closest larger integer. So here I'm going to apply math.ceiling to this whole expression such that it always will return a integer. So hop length equals 3. This will become the closest integer. There we go. Now let's see if we can get the length of the data set. We can. So when we want to index into our data set, we should be able to start from 0 all the way to length of the data set -1 and get different window size chunks of our audio, and each consecutive index would be hop length apart. The way we can do this is to set our get item. So our get item should get, let me put the documentation here. So it should receive IDX. So let's call this the input, IDX of the chunk from 0 to length of the object. And it should output audio chunk in as tensor. So it's good to write the documentation before you do it to see what you need to receive as input and what you should return. It kind of makes it clear. Okay, so I have the index of a chunk from 0 to the length of the data set. I can now use torch audio.load, which we used before, pass in the self file name and call it a chunk. So a chunk of audio would be self. But we need other arguments too. What is the frame offset in this case? So frame offset in this case would be how much to skip in the audio file. So if we start out in the beginning, the index is 0. Let's go back to the illustrations here. If we start out, if we have K2 as 2, for instance, from the beginning, the IDX is 0. We start here. That's our offset. If IDX is 1, that's the second element in our data. We start here with the offset of 2. If the IDX is 2, the offset would be 4. So it seems like the offset has a step size of stride, goes up as much as stride or hop length. So I can say, well, use self.hop length times the IDX. So for the 0th index, offset would be 0. For the index 1, it would be hop length, in this case 1, and so on. Also, it's also important to create documentation for the units we're using here. When we do initialization, the window size and the hop length, we need to specify it and keep it consistent in our code, whether these are measured in seconds or frames. I will say these are in frames for now. We can take the input as seconds and turn them into frames. That's just a simple multiplication. But for now, let's assume these are frames. So chunk of the audio file would be read this file name. Do not store the whole thing in the memory. Offset by hop length times the index. And the next argument would be number of frames. So number of frames in this case is simply my window size. How much do you want to read? So window size is the number of frames. Now this could happen that you're at the end of the audio file. So the offset plus the window size would not be there. That's the end of the audio file. That's the final part that we decided to keep. Let's see if PyTorch gives us an error or it can handle it itself. Other arguments, I'll keep normalized to true as default. Channel first true, that's good. Yeah, and we don't need to change anything else. So we get this chunk of audio as tensor and we would basically return. We could have done it in one line of code as well. All right, so let's create our data set. Let's get the length of the data set, window size 3, hop length 3, and let's have one index into the data frame. So let's start with the first index. So it's just 2 channels, each one 3, basically 3 samples. Now it's good to unpack this chunk. So it says tensor chunk and sample rate. It returns a tuple. You might not want to return the sample rate here. You might want to store the original sample rate as an attribute. So you can say self.metadata equals, self.sample rate equals self.metadata, and you get the sample rate, 48,000 in this case. Let's see, 48,000. Okay, so let's do a double check. Number of frames, what is the data set sample rate? 48,000. Length of the data set, basically divided by hop length. The first sample is just a really short audio segment of only 3 samples. It's going to be inaudible. And then you can get your data set sample rate like so. Okay, now let's listen to a chunk of audio and see how it sounds like. Right now the audio is pretty small, the window size. I can increase it a bit. Since I already have the sample rate, 48,000, I can say, give me a 3-second chunk of it. 3 times 48,000. That's my window size in samples or frames. And do a hop of 2 seconds. So jump every 2 seconds, start from 0 to 3rd second, then go to second 2 up to 5 seconds, second 4 up to 7 seconds, and so on. So now the length of my data frame is basically 8,781. Okay, so I can get the first index of my data frame. This is this tensor. Let's get the shape. 2 by 144,000. That's basically what 3 times 48,000 is. I have its sample rate, so I can use the audio class that I loaded, and it's going to take an NumPy array, or it works with Torch tensor, and you can say, please display this sample of audio, and I need to say what the rate of audio is, what the sample rate is, and it's going to show here. Let's listen.
Talk like the other shaman in neighboring tribes.
Okay, that's the first one. Let's see the second one. It should jump 2 seconds.
Other shaman ate the yellow.
So you saw that the first chunk was overlapping with the first chunk. So second chunk was overlapping with the first chunk. Let's make it overlap a bit more. So let's decrease the hop length to 1 second only. If I now run this, the first segment would be
talk like the other shaman in neighboring tribes.
So it ends at neighboring tribes. Here, the next example.
Other shaman in neighboring tribes.
And then if we go index 2, it's going to hop again 1 second. Great. So we basically accomplished what we were looking for. Our goal was to create a large audio set dataset class that would take a file name, a window size or the chunk size, and a hop length to optionally do overlapping segments. It would take an audio file name as input, use Torch audio to extract sample rate, length of the audio, and it would get a specific chunk of audio and return it. Now, if you don't want overlapping segments, for some cases, like cleaning audio files, you might not want to have overlapping segments. For others, like doing transcription with the Whisper model or the Wave to Vec models, you might need overlapping segments to do more accurate transcriptions. But if you don't want overlapping segments, you can basically copy paste the same thing here. So window size should be equal to hop length. So it means after it captures a chunk of audio, it will skip the same amount of that chunk and use a non-overlapping segment. Let's try this one out. So I will look at audio dataset 0 index.
Talk like the other shaman in neighboring tribes.
So it ends at tribes. The second one.
Other shaman ate the yellow-spotted mushroom.
Other shaman. Okay. So there's no overlap now. So it's pretty customizable. The next step is to create a data loader. We'll use PyTorch's data loader because it can let us do multi-processing by setting a number of workers. And it's pretty straightforward. So I'm going to go up here and say from torch. So that's my data loader class. It's pretty convenient. You can basically give it the data set. The only constraint it has on the data set is that your data set should have this len method to get the length of the data set and this get item method. That's pretty much it. You can create a custom data set, which we did here, or use one of the PyTorch's built-in data sets, which it's not as customizable as what we did here. But let's create a data loader and let's call it DL. So my data loader should take a batch size, so we can set an initial batch size here. Batch size is, let's say, 64. And it will collate and collect 64 chunks of tensor, stack them up together, and return it to us. Okay, so first I need to pass my data set, which I created here, called dataset. That's the first argument. The other arguments are optional. By default, it's doing a batch size of 1. I want 64 in this case, so I'll pass my batch size. You can set the number of workers to more than 1. In some systems, especially for Windows, it could be a bit tricky, but I'll set it to 4 to use 4 threads on my CPU to make it faster to load. Especially since we're doing I/O, reading from disk. Each time that we are asking for a chunk, we're loading a portion of this audio from disk. It can get pretty slow. So using multiprocessing when you're doing batching with like 4 processes at a time can give us approximately 4 times speed up. So I'll set the number of workers to 4. It's an experimental number based on your CPU. You should try out 0, 4, 8, etc. See which one's faster. For collate function, we don't need to do anything special, and also for drop last. Drop last says if the last segment is less than 64 items, should I drop the whole segment? And we say no. All right, this is my data loader. It's an iterator, so if you have a look at it, it's a Python generator. So each time you ask for something in it, it's going to give you a chunk of audio. Let's check one thing though. Shuffle is none or false by default, so it's not going to shuffle your data set or scramble your audio file. Depending on your application, you want to keep the order of the audio. That might be something that you want to do. So iter on the data loader is going to give you a generator, and if you ask for the next item, it's going to give you a batch. So let's have a look at the first batch. Okay, so it's taking a while here. Probably is firing up multiprocessors. It says data loader worker exited unexpectedly. So let's see what happened here. If you face any bugs, first set the number of workers to 0 to hopefully get a better, kind of more interpretable solution here. So right now, it seems that it's working with number of workers 0. So I can get a batch, have a look at my batch. We'll come back and explore what the number of workers and what kind of issue that causes. So my batch is a tensor, floats, looks right. I can get the shape, and it basically looks like a piece of audio. It has 64 samples of audio, 2 channels each one, and 144,000 samples. So if you look, we can look at each one of these separately. So I can say audio, give me batch 0, the first one in the batch. Let's see what the error is. Oh, I need to pass the sample rate, of course. So dataset.sr 48,000. It says the handle is invalid. Let me double check everything here. 48,000 batch 0.shape. Okay, this looks right. So for some reason it says it's trying to load it from a file. Let me see if we can debug this. So what it's doing is trying to load this torch tensor from the file. It's trying to get the file name that we passed to it, which is none right now, and try to load that. It's probably one of the checks in the audio class did not pass. Yeah, because I forgot to put the rate here as a keyword argument, so it thinks it's a file name, this data SR. So that's my mistake here. Okay, we get these 3-second audio.
Talk like the other shaman in neighboring tribes.
So this is the first segment in the batch. This is the second.
Other shaman ate the yellow-spotted mushroom.
And so on and so forth. So we successfully created a batch of data that each would contain 2 channels and 144,000 samples, which is our window size. You can try to debug this issue where we set the sample number of workers to more than 0 and see why you get this issue of worker ID not responding. It's probably because it's trying to read from the same file using multiple processors at the same time. And on Windows, you're not allowed to do that, so it's going to kill those processes. So this could be, for now, one of the limitations of this method, that we cannot create multiple processes which at the same time in parallel open the same file and read different chunks of it. So we can later create a workaround for this. But that's pretty much it. We created a large audio data set that would take a file name and return a batch of arbitrary size, in this case 64 of audio samples. In the next ones, we'll look at how to do audio classification, anomaly detection, audio generation, and so on. Thank you very much.